Today I'm going to be trying giving some intuition on the power rule in calculus, which is this formula here. The derivative of x to the n is n times x to the power of n minus 1. Now before I get started, I want to talk about the notation of dy over dx. Right now we know this is slope, but what's so special about this from what we learned in grade 9, such as delta y over delta x? Right, these are all equal to slope, except this one is tangent and this one is between 2 points. Well, you could think of dy over dx as delta y over delta x, limit as delta x approaches 0, right? So dy over dx would equal to limit as delta x approaches 0, of delta y over delta x. You can more clearly see this when you are given the first principle, when you're first introduced to derivatives, right? This formula right here. This is basically delta y on the top, and the bottom is x plus h minus x limit as h approaches 0, right? That is a derivative by definition, and you can see that it's basically the same thing as this, right? My difference approaches 0. Now, how does this notation help me when using the power rule? Well, I kind of want to first start off with an example of x squared, right? So imagine I have a function x squared, but instead of representing it as a parabola, I'm going to represent it as an actual square, a physical square, right? And we are saying x squared. And I'm saying, okay, well, this side length is x, this side length is x. If I increase my x's by just a little amount, I'll call this dx, what will my difference in y be, right? So let's try and calculate that. Well, you could see that this shaded region right here is actually just x times dx, right? And you could see that this shaded region here is also x times dx, right? So we have another x plus dx here, times dx. What about this little square here? Well, that's just dx squared, right? So we write it like so. But what you notice is that because my dx approaches 0, this little square here will approach 0%. And you can actually visually see this. If you make it very, very large, you'll notice that this dx squared will actually take a larger amount, like a larger percent of my dy. For example, let's say I made my dx super large, like this big, right? You can see that this dx squared portion here, well, that's like maybe a fifth of my total dy. But if I make this little portion very, very small, this dx very, very tiny, you'll notice that it actually approaches 0% of my total area. This is like maybe 1/20th out, and then as it approaches 0, as my dx approaches 0, this little dx squared will approach 0 a lot faster, right? So with that in mind, I'm gonna erase this dx squared, right? I'm just gonna consider it as 0, and this would be equal to dy. And then we collect like terms. We say that 2x times dx would equal to dy, and we simply move the dx to the other side, and we see that dy over dx would equal to 2x. And this agrees with our power rule, right? Let's say I had x squared, and I took the derivative of this, d of dx. This would equal to 2 times x to 2 minus 1, which equal to 2x. Now, this is just one example, right? This is x squared. What if I want a more general example, right? Let's say I had the function y is equal to x to the power of n. Well, what happens if I add a tiny nudge in x? I'll get a tiny nudge in y, right? It'll become y plus dy equals to x plus dx to the power of n. And we could use binomial expansion to expand this. If you don't know what that is, I suggest you to do some research on the Pascal's triangle. But what we'll see is when we do expand this will actually equal to y plus dy. And the first term would be x to the n. The second term would be x to the n minus 1 times dx. And then there's it in front, and it'll keep on going, some random coefficients, but the exponents will always kind of add up to n. And then my last term, or actually I'll start with my second last term, would be n times dx to the n minus 1 times x plus dx to the power of n, right? And using the similar logic we used previously about the square, we'll see that when dx does approach 0, all of these will also approach 0% of them, right? So I'm just going to cross them out to be 0. And then in the end, what we have is y plus dy would equal to x to the power of n plus n times x to the n minus 1. Now we define y to equal to x to the n, so we cancel these out because they're equal to each other, right? We subtract y from both sides, and they kind of just be equal to 0. And now we're left with another function. dy would equal to n times x to the n minus 1 times dx. And we divide both sides by dx, we see that dy over dx would equal to n times x to the n minus 1. I hope that gave you some intuition on the power rule. This is in no way, shape, or form a rigorous proof, but it does give you a sense of idea as to why we do things.